This is another video related to my current Raspberry Pi project for controlling a model railway using CBUS. In my previous video, I explained some of the problems with performance and how I overcame them. In this video, I'll be covering an earlier challenge, which is how I learnt the protocol first, which was required before I started actually doing any coding. I'm going to start with a brief introduction about the reason for a layout control bus and an overview of what CBUS is. I'll then explain about how I learnt about the protocol, how it works, and how to use the software to send and receive information onto the CBUS. I'll then explain about the Python libraries that I created to interpret the CBUS messages. A layout control bus is a method for connecting different modules using a single electrical bus. It greatly simplifies wiring by needing only 3 wires, or 4 if you include power, between the devices. This is particularly useful when creating a modular railway layout, as it reduces the cabling between the modules. In this case, there is one cable with 4 connections for the layout control bus, and there's another with 2 connections which is used for connecting the tracks together. That is much less than if I had to wire each of the sensors across the board. It just so happens that another industry had a similar problem and came up with a solution. If you think about older cars, then there would have been a wire going to each of the devices in the car. So there's a wire that went from your indicator stick to the lights on your front right and rear right of the car, and then the same to the left hand side of the car. As more technology has been included into cars, then think about all the different sensors, lights and actuators, each having its own wire, and the number of wires would be immense. Bosch came up with a solution called CAN bus. This creates a bus that can be used to pass messages around the car. It provides two-way communication between devices, ensures reliability, and includes prioritization so that important messages such as apply the brakes are not delayed. CBUS was created for model railways and essentially takes CAN bus and adds some protocols specific for controlling model railways in what's known as a layout control bus. There is a further development which is known as VLCB, or Versatile Layout Control Bus. It is essentially the same as CBUS, but with extra flexibility for future expansion. It can fully interoperate with CBUS, and I'll be referring to CBUS, but this is just as relevant for VLCB as well, and whilst the code is really for CBUS at the moment, I've called it VLCB with the intention of supporting that in future. As with other bus technologies, there needs to be a way of knowing what to do with the messages and whether they are intended for each device. In CBUS, this can be achieved using 2 different methods. The first is the producer and consumer model, where each producer creates an event and consumers listen for those events. This allows consumer devices to learn the events they want to respond to. The other is address mode, where each node needs to be configured with a node number and then a device numbers for individual events. These can be configured in short address mode, where it's just the device number used to identify the events, or long address mode, where the combination of the node number and device number are used. I've already explained these in another video. See the link in the description. So in this video, I'm going to concentrate on the software side. There is some software which can be used to control CBUS, including JMRI, the Java Model Railroad Interface, and MMC Server. But I didn't want to just use existing software, I wanted to create my own. I did consider using the API which is included in JMRI, but in the end I decided to control the hardware completely using my own code. These applications are still relevant. They help me to understand the protocol better, but also I haven't provided a way to configure the devices, only to communicate with them after they've been configured. So you may need to use these to configure the devices and your CBUS network first. I've included all the opcodes required for the configuration, but I've just not implemented them yet, so it is something I could potentially do in future. But this is what the MMC software is really intended for. It's a particularly useful tool for configuring your network, so I recommend using that for the configuration. The challenge I set myself was to get my Raspberry Pi communicating with a CAN USB 4, and then creating the software that allows me to control the railway. The connection is through a USB port, so effectively it's how to communicate using serial communications using USB. And that's something that is well supported by software libraries. I just need to understand what messages I need to send over the USB. As I've mentioned, there is already some open source software, so I started by reading the source code for those. They weren't in the programming language I was intended to write in, and because of the complexity of the software, I didn't really get that far. I decided it would be easy to start from scratch rather than trying to base on those existing code bases, but I did find some useful information about the opcodes, which would be useful in the next stage. And this shows some of the source code from the MMC server. You can see the opcode as well as the hex code and some useful comments, and that would become quite relevant later. So next I did some packet sniffing with Wireshark. You may be more familiar with Wireshark as a way of capturing network traffic, but it can also be used to monitor USB traffic as well. I've already created another video that explains how you can use Wireshark to monitor USB, although that was used to monitor a laser cutter rather than the model railway. It's just as relevant here. I exported the data from Wireshark and used some simple scripts to filter out the data so I could see the string that was being sent to the CAN USB 4. What was useful is that I could see the addresses and the opcodes in the packets, which I already knew from the earlier step, so this gave me an idea of what the data included and perhaps how it was formatted. I now had enough information to send commands to and from controllers and get an idea of the sequences. This was really useful and could have been used to create replay type activities, but didn't really give me enough to understand the protocol. And part of the reason for this is that some of the fields are shared or store data in different ways. For example, the priority and CAN ID share a single byte, which makes it difficult to understand. It gets more complicated when related information is presented in different ways. So I was able to put some information together, and I put it in this format to help me understand this a little better. The useful bits was seeing the opcodes, which is this hex number, which is after the character N. And I could then look up those, and I've put in the comments the opcode and some of the comments that I got from the source code I mentioned earlier. I could also deduce some other information, such as this 012C and 012D. These are hexadecimal representations for the number 300 and 301. And this matches the module addresses that I'd allocated to the CBUS modules, so I already had an idea that that was some addressing involvement in there. But some of the information is encoded in a form that I was not able to see directly. The information on the left of this N character is called the CAN header. It's 11 bits long, but padded to 16 bits using zeros. But it uses those 11 bits for both the CBUS ID and the priority. As there are only 7 bits of data for the CAN ID, it doesn't fall on a convenient byte boundary, so it's not that easy to decipher. Also, the padding is the least significant bits, which, if you write it down as a binary number, are the digits to the right. That's not a problem for the electronics or the code that need to use that data, but it makes it harder to decipher by a person without understanding the protocol in advance. The light bulb moment came when finding the developer's guide. The file is difficult to find using search engines unless you know that specific file exists. I eventually found it when I was in the documents directory in the MMC server source code, and there's a copy of it stored in there. This is a good document which explains the different fields and values. It does, however, make some assumptions about knowledge of CBUS fundamentals as well as the NRMA DCC protocols. As an author, I understand the challenges of trying to target documentation for the right audience. I do think this is fairly good, but I don't think I would have been able to go straight from this to an implementation. When combined with the reverse engineering and importantly the packet sniffing from the previous step, I finally started to understand how the CBUS protocol worked. With a bit more research looking at DCC and some historical forum discussions, I was able to figure out what I needed to know. I created some Python classes which included all the possible opcodes and some code to read and generate the appropriate codes for the strings. By looking at these using Python, I was able to read the message codes as well as see the value of the address fields, etc. And so I created a console, a simple GUI using Python Pyside 6, which is a GUI framework based around Qt 6. This allows me to send and receive messages onto the CBUS as well as monitor for other messages. I started by issuing the command using another controller. After looking at the process flows in the console, I could then understand the opcode and what it was doing. Looking up the details in the developer's guide gave me the details of what other fields I needed. I've then created the start of a GUI application. I've already covered this in my earlier videos I mentioned previously. It still needs a lot of work before it would be a complete application, but it's enough to control accessories and a loco. I've now implemented the function buttons as well, so it's possible to control the sounds of the loco as well as to control its speed and direction. Hopefully that's given a bit of an insight into how I was able to learn a new protocol and implement enough code to send messages onto the CBUS. If you found this interesting, please give the video a like. I'm going to continue to work on the project and I hope to provide another update in the future. So if you haven't already subscribed, please click on the subscribe button. Thanks for watching. I look forward to seeing you in a future video.